In a gas turbine engine, the air is drawn through the intake by a compressor, which is attached to the main shaft. At the end of the shaft, the turbine is attached. Air drawn through the intake by the compressor will increase in pressure and temperature as it passes through the compressor stage of the engine. However, the successive increases and decreases in velocity practically cancel each other out. Air leaves the compressor and passes to the diffuser, which converts the velocity energy to pressure energy. On leaving the diffuser, the air passes into the combustion chambers. Of the total mass of air passing to the combustion chambers, approximately 25%, known as primary air, enters the flame tubes through the flame tube orifice and is used for combustion. The remainder of the air passes along the outside of the flame tubes, entering through dilution holes in the side of the tubes, and is used for cooling. Each combustion chamber is equipped with a burner containing a swirl-type atomizer, and through the atomizer the fuel is injected under pressure by the fuel pump into the combustion chamber, where it mixes as fine droplets with the incoming primary air. The combustible mixture formed is ignited by the igniters in 2 or 3 of the combustion chambers, depending on the design of the engine. On completion of the starting cycle, the igniters are cut off. At this stage, we can say that we have light-up. From this point, combustion is continuous, and the pressure in the combustion chamber for a given fuel flow is constant. The residual or secondary air, which passes through the dilution holes into the flame tube, mixes with the main mass of burning gas and cools it sufficiently to permit it to pass through the turbine at a temperature within the safe limits of the turbine material. Within the combustion chamber, owing to the added heat energy of the fuel, the gas both rises in temperature and increases in volume. After passing through the combustion chambers, the hot gases enter the nozzle guide vanes, which direct them at increased velocity onto the turbine blades, causing the turbine disc to rotate, which in turn drives the compressor. Of the total energy, approximately 60% is used driving the compressor, so that there is a considerable drop in gas pressure and temperature across the turbine. The remaining 40% of the energy, after driving the turbine and the compressor, is used to form a high-speed jet, which has a substantial residual pressure. This jet passes into the exhaust cone to emerge close to atmospheric pressure at the orifice. The jet not only has kinetic energy owing to its velocity, but also has substantial heat energy. However, the heat energy is released to atmosphere and is consequently wasted.